Hi everyone, I'm Tassos. I'm an associate professor in architecture and machine intelligence at the Bartlett School of Architecture. And kind of the overall idea of this presentation is to give you a glimpse of how we are working to encode qualities of space in databases into data sets so that we then can work with kind of ML and deep learning models, right? Well, to be honest, coming here and talk about, deep learning models today that we've got with us, Piotr from DeepMind is a bit of a blasphemy. But, let me speak about my little shallow models. So I'm both an architect and a trained computing engineer. I still think I'm the only one in the school that has this kind of worked on both sectors professionally. So after becoming a professional architect in Greece, I joined the Imperial College computing department where I focused on artificial intelligence. I don't think kind of at the time we were using buzzwords like ML. We used to do kind of pen and paper sigma backpropagation calculations, everything by hand sometimes. I don't know, for torturing probably students and us. So my passion for the digital side and space syntax came early in my studies in architecture. I was fascinated with space and visual illusions, and I started using hybrid digital augmentations in order to create cool exhibitions and kind of physical experiences in order to challenge the kind of understanding of spatial perception. So this is how I became familiar with the work of the Space Syntax Lab at UCL. I joined the lab 13 plus years ago full time, and my personal focus is on developing new theories and methodologies for the computational analysis and synthesis of space. Kind of these are some of the things I've done and during my time. Augmented visibility analysis and 3D VGA, kind of methodologies I developed. And kind of my focus, of course, isn't always kind of human-centric, around the human-centric space, like the kind of agent-based model on the right. Um, but I've also worked kind of in cross-disciplinary projects, like creating a new 3D surface-based model of VGA in order to work with ant colonies, ant nests, as the example on the left. While most of the work we do with my team and other colleagues is all about kind of numbers and code, we try to find cool ways to disseminate our ideas. So we have kind of exhibited and presented our work at a number of international events. This was part of the Mutations slash Creations mural exhibition at the Museum of Modern Art Center, Pompidou Center in Paris, where kind of I think I probably got the original COVID. This was 2 weeks before the first lockdown, the proper lockdown. We presented at the Ars Electronica together with our research students, Biennale, and we have a good spot on the kind of upcoming the Architectural Design magazine. So kind of a shameless plug for our lab. The Space Syntax Lab was created by Bill Hillier back in the 80s. And kind of we're the most research active lab in the faculty with kind of major research grants and kind of top marks during all of the previous research excellence benchmarks that the university has to take every kind of 4 or 5 years, if I remember correctly. We also run 2 postgraduate courses and a very large PhD program. So if you want to ask me about something about this or kind of future students and stuff, please feel free. So let's get into kind of the main part of the presentation. The presentation will move from the kind of established data representations that we use in the field to a new one that I'm exploring with a couple of colleagues. In the end, I have a couple of kind of slides with projects that we're working with kind of research students. So if you're not familiar with the concept of space syntax, kind of in the basic ideas of spatial complexity and how we are reading it from kind of through graphs, of course, we've got a couple of books about it, not well, by our founder, Bill Hillier, and I'll explain a couple of things, of course. So some basics that are the foundation, both of what I would call kind of an aggregation model like space syntax and the decomposition models that we're going to see later on. So space syntax studies cities space first. That is by looking first at the street networks and kind of at kind of first sight, they seem to be incredibly complex and disorderly. It's not clear what we can say about them or if we can say anything about them at all. But looking at space around us through movement, kind of visibility, and kind of basic morphology, we can start building some interesting ideas. Of course, we need to start from kind of the architect's point of view, especially if you ask me. And they're like, we have two core ideas, right? The space is vital for human activity, not a background to it. And space is fundamentally a configurational entity. So cities are large collections of buildings held together by a network of space or kind of the street network. The network is the largest thing in the city and is what holds the city together. And of course, kind of it has a structure, it has a certain geometry, a topology, and a certain pattern of connections. These are probably the sentence that describes everything I do in a way, and what you'll see in a couple of slides down the road. Traditionally, evaluation of spatial networks is done using numerical comparison of spaces with metrics such as global and local space syntax measure, of course. So here's what kind of an interpretation of a graph model looks like through the eyes of a space syntax analysis. This is the space syntax value of integration for every street segment in London. From a graph theory point of view, this is equivalent to closest centrality. So if you're into graph theory, the closest kind of measure is closest centrality. So you see how with just knowing a network kind of simple kind of xy lines, it's just an x1 y1 x2 y2 line, we pick up Oxford Street as the most integrated street in London. Again, in simple terms, the logic behind the space syntax integration is that on average, we remember how to navigate to a place based on the angular complexity from origin to destination. Of course, in this case, the average, right? The average. So Oxford Street, on average, is easier to navigate from every other location in London, kind of to Oxford Street, right? So red means that the street is more shallow to the network, right? Upper in terms of categories, whether it's hard or easy to navigate to or to remember the navigation pattern to there. So now let's discuss how we think of kind of spatial complexity. To produce data like this, we need to have kind of a clear cost or a way to calculate. The most basic one is the metric distance. So the Euclidean distance in meters from one space to the other, or kind of one street segment to another, right? So blue represents low values, red is high. And we see here, I mean, some certain kind of morphological complexities for some areas to be a bit more segregated in different kind of distance definitions, right? In this case, I mean, with the metric distance is usually quite uniform. The center of attention, let's say the point zero there in the graph, and the next one is the Bartlett School of Architecture in London. And here we've got the angular distance. The angular distance from one space to the other, again, from the Bartlett School of Architecture. So we measure this by calculating the deviation between the street we are now on and the next one that we want to move to. Okay, so that's the angular change, and that's the cost metric. So, well, there are a lot of colleagues in the research community that have extensively discussed and kind of linked angular-based morphologies with the way that people perceive the complexity of space around them and how they navigate. So there's kind of the literature is very, very long. Again, values blue are as low, red is high, and here is way more prominent the way that we see how certain morphological complexities force areas and neighborhoods to be severely more segregated than the next door, let's say, neighbor. Now, let's take this kind of last concept and keep it in our minds for kind of the most of the presentation. In almost all slides, I like you to think how you experience and map the complexity of the area around you, with the center being your own position every time, right? So the center of attention is always you. As you move through the network is always around you. So let's talk about kind of spatial decompositions. So think about the local area around your house. We can kind of deconstruct and assign a value, okay, admittedly a very complex value, to the geometric arrangement of the closest streets to your house. Let's say 100 streets, 200 streets closest. The magic with this is that we can describe every micro detail of this topogeometry of this small graph around you, right? So over the same, let's say, general area, by moving the center of attention, we can create a different spatial representation for each morphological experience. And this results in a slightly different geometric representation as well, right? This happens because we see each small area around us as a small subgraph that we take crack out of the main system. And the idea of converting a graph representation to a set of numbers involved kind of methods relating to kind of graph spectra and eigen decomposition, right? So graph spectrum is a set of order eigenvalues of the adjacency matrix of the graph, of course, and it provides kind of a feature vector that directly captures the structure of that graph or subgraph, let's say. Each graph has a different spectra, and almost all graphs have unique spectra. So let's talk about spectral integration. Using these raw data for every street in London, the first thing we can clearly quantify is how structurally similar areas are or how unique they are. Kind of a note here, right? We're talking about pure topogeometry here. No space syntax, no shortest path, no movement analysis from origin to destination, right? It's the topogeometry around that area, let's say the center of attention plus the subgraph around it. So our initial intuition drove us to kind of generate a Euclidean distance integration model of all data points to all others. Kind of understanding the kind of clusters of kind of close proximity in spectra, we could identify a special form of spectral integration that can be evaluated as a uniqueness analysis, kind of spatial morphology. So this map describes the differences in local morphology that each area has on average from all other areas of London. Deep purple represents areas that are very similar to each other, and in essence represents areas that can be identified as kind of looking like typical London neighborhoods. So the white color shows areas that have very unique topogeometric characteristics, which sets them apart from kind of the purple ones. But just a clarification here that two areas in white, they're both marked as white, don't have similar kind of unique characteristics by the definition, right? They can be outliers from completely different directions of this kind of multidimensional point cloud. So if you're kind of familiar with London, you'll see kind of new developments on the east near Stratford. These are definitely not London looking, typical London looking. So what we would call, let's say, typical London looking neighborhoods are kind of crescents, Victorian kind of houses and terrace houses, and places that you typically see in kind of a period London movie set, right? The next step was to use kind of a supervised clustering techniques. We can build kind of groups of areas with similar internal morphology. This is possible because the raw values purely describe the topogeometric structure of its sub-area of the road network. So, this is London classified in three clusters of topogeometric similarities. I mean, you could see here the essence of the foreground and background network here, which is traditionally something that Bill Hillier worked kind of a lot. This is of course something fundamentally linked to space syntax, but kind of here we expose it through a different method. Another super cool finding from this is kind of the depiction of the kind of foreground network penetration to the surrounding local neighborhood or kind of the back streets. This kind of varying degree of high street expansion is something that we can't really, well, easily, let's say, see with other analysis. So my work is focused on building model like this, kind of in massive scales at the moment. Um, from an analysis point of view, we currently work on models understanding how the nature of some inter or intra-regional questions are represented in these kind of models. Also, we believe that detailed mapping of clustered morphological similarities could address challenges of interdependency or spatial isolations of cities, councils, neighborhoods around the UK. I mean, for example, here. And you see here in the on the circle, this is the English town of Milton Keynes. It's always a weird outlier in most most analysis that we do, and it's a designed new town, let's say, right? So it has always a very unconventional spectral structure, and whenever we tell local kind of authorities or experts about this, they say, "Oh, yeah, that's obvious." So this is another view of Greater London with kind of interesting patterns. So internally at the moment, we are investigating deep learning techniques for spatial transfer learning, and this kind of spatial data extraction has helped us a lot. So this is how it looks up close. So kind of to finish up, I've got a couple of projects that we did together with our research students. We try to kind of give them project ideas, kind of tools and methods that create the kind of exciting potential for them, and they're also giving them kind of insights of what we are working as well in our own personal research. So one project, for example, was the identification of local community segregation by complex transportation structures. So there was an automatic pattern recognition all over the UK. So this one, we are trying to bring the knowledge we gained from primary kind of space syntax models and link it with kind of more current deep learning methodologies in order to augment the street topogeometry and the understanding about it, as you can see here. Here there are elements kind of expanding on the local high street penetration that we talked about a couple of slides back. This was more kind of an elementary reinterpretation of kind of that metric all across London, in this case, again, using government data. And here we're kind of, following the government supply data set for the London high street activity. Kind of in the end, the output is usually kind of a super interesting multi-layered data set, kind of an analysis of it, and we aim to also kind of request kind of concept proposals that might come out of analysis like this, right? Another plug is that we are very good with kind of open source, and we support the open source community and both practitioners and commercial and businesses and other architectural offices. We have our own open source graph analysis, network graph analysis tool that works across scales, does visibility graph analysis, all the space syntax measures for kind of urban analysis, an agent-based model, and its source code is uploaded online. It's C++, hard to, it's a bit not the best kind of style of writing and documentation, but it's really good. And if you have anything, if you want to contribute, come and find me. We open sourced it, and I lead this project. We open sourced it like back in 2011. So that's it from me. If you've got any questions about the presentation or the things we do at the Space Syntax Lab, urban design, MARC, especially NEML specialization, Machine Intelligence Lab, and anything at the School of Architecture, email me. Cheers. Thank you.